Chapter 1. Units and Measurements. Introduction. Physics is a quantitative science where we measure various physical quantities during experiments. In our day-to-day life, we need to measure a number of quantities, example, size of objects, volume of liquids, amount of matter, weight of vegetables or fruits, body temperature, length of cloth, etc. A measurement always involves a comparison with a standard measuring unit which is internationally accepted. For example, for measuring the mass of a given fruit, we need standard mass units of 1 kg, 500 gram, etc. These standards are called units. The measured quantity is expressed in terms of a number followed by a corresponding unit. Example, the length of a wire is written as 5 m, where m, that is meter, is the unit, and 5 is the value of the length in that unit. Different quantities are measured in different units. Example, length in meter written as m, time in seconds written as s, mass in kilogram written as kg, etc. The standard measure of any quantity is called the unit of that quantity.
System of units. In our earlier standards, we have come across various systems of units, namely, first, CGS, centimeter gram second system, second, MKS, meter kilogram second system, third, FPS, foot pound second system, fourth, SI, System International. The first three systems, namely CGS, MKS and FPS, were used extensively till recently. In 1971, the 14th International General Conference on Weights and Measures recommended the use of International System of Units. This International System of Units is called the SI units. As the SI units use decimal system, conversion within the system is very simple and convenient. Fundamental quantities and units. The physical quantities which do not depend on any other physical quantities for their measurements are known as fundamental quantities. There are 7 fundamental quantities: length, mass, time, temperature, electric current, luminous intensity, and amount of substance. Fundamental units. The units used to measure fundamental quantities are called fundamental units. The fundamental quantities, their units and symbols, are shown in this table. Derived quantities and units. In physics, we come across a large number of quantities like speed, momentum, resistance, conductivity, etc., which depend on some or all of the 7 fundamental quantities and can be expressed in terms of these quantities. These are called derived quantities, and their units, which can be expressed in terms of the fundamental units, are called derived units. For example, SI unit of velocity, unit of displacement upon unit of time is equal to meter upon second is equal to meter per second. Unit of momentum is equal to unit of mass into unit of velocity is equal to kg meter per second, which equals kg meter second raised to -1. The above 2 units are derived units.
Supplementary units. Besides the 7 fundamental or basic units, there are 2 more units called supplementary units. First, plane angle d theta, and second, solid angle d omega. First, plane angle d theta. This is the ratio of the length of an arc of a circle to the radius of the circle as shown in figure. Thus, d theta is equal to ds upon r is the angle subtended by the arc at the center of the circle. It is measured in radian, written as RAD. An angle theta in radian is denoted as theta radians. Second, solid angle d omega. This is the 3-dimensional analog of d theta and is defined as the area of a portion of surface of a sphere to the square of radius of the sphere. Thus, d omega is equal to dA upon r square is the solid angle subtended by area dA at O as shown in figure. It is measured in steradians, SR. A sphere of radius r has surface area A pi r square. Thus, the solid angle subtended by the entire sphere at its center is omega is equal to 4 pi r square upon r square is equal to A pi SR.
Example 1.1. What is the solid angle subtended by the moon at any point of the earth? Given the diameter of the moon is 3,474 kilometers and its distance from the earth is 3.84 multiplied by 10 raised to 8 meters. Solution. Solid angle subtended by the moon at the earth is equal to area of the disk of the moon upon moon minus earth distance the whole square, which is equal to pi multiplied by 1.737 multiplied by 10 raised to 3 the whole square upon 3.84 multiplied by 10 raised to 5 the whole square, which is equal to 2.045 multiplied by 10 raised to minus 5 steradians. Do you know the relation between radian and degree is pi radians is equal to pi radians is equal to 180 degrees. Therefore, 1 radian is equal to 180 upon pi is equal to 180 upon 3.1415 is equal to 57.297 degrees. Similarly, 1 degree is equal to pi upon 180, which is equal to 3.1415 upon 180, which is equal to 1.745 multiplied by 10 raised to minus 2 radian. 1 degree is equal to 60 minutes. 1 minute is equal to 2.91 multiplied by 10 raised to minus 4 radian. And 1 minute is equal to 60 seconds. 1 second is equal to 4.847 multiplied by 10 raised to minus 6 radian.
Conventions for the use of SI units. 1. Unit of every physical quantity should be represented by its symbol. 2. Full name of a unit always starts with smaller letter even if the name is after a person. Example, 1 Newton with small n, 1 joule with small j, etc. But symbol for unit named after a person should be in capital letter. Example, capital N after scientist Newton, capital J after scientist Joule, etc. 3. Symbol for units do not take plural form. For example, force of 20 Newton and not 20 newtons and not 20 ns. 4. Symbols for units do not contain any full stops at the end of recommended letter. Example, 25 kg and not 25 kg full stop. 5. The units of physical quantities in numerator and denominator should be written as one ratio. For example, the SI unit of acceleration is meter per second square or meter space second square, but not meter per second per second. 6. Use of combination of units and symbols for units is avoided when physical quantity is expressed by combination of two. Example, the unit J per kg K is correct, while joule per kg K is not correct. 7. A prefix symbol is used before the symbol of the unit. Thus, prefix symbol and units symbol constitute a new symbol for the unit which can be raised to a positive or negative power of 10. 1 ms is equal to 1 millisecond, which equals 10 raised to minus 3 second. 1 mu s is equal to 1 microsecond, which equals 10 raised to minus 6 second. 1 ns is equal to 1 nanosecond, which equals 10 raised to minus 9 second. Use of double prefixes is avoided when single prefix is available. 10 raised to minus 6 second is equal to 1 microsecond and not 1 millisecond. 10 raised to minus 9 second is equal to 1 nanosecond and not 1 millimicrosecond. 8. Space or hyphen must be introduced while indicating multiplication of two units. Example, meter per second should be written as meter space second raised to minus 1 or meter hyphen space second raised to minus 1 and not as ms raised to minus 1 without any space in between, because ms will be read as millisecond. Measurement of length. One fundamental quantity which we have discussed earlier is length. To measure the length or distance, the SI unit used is meter, written as m. In 1960, a standard for the meter based on the wavelength of orange-red light emitted by atoms of krypton was adopted. By 1983, a more precise measurement was developed. It says that a meter is the length of the path travelled by light in vacuum during a time interval of 1 upon 299,792,458 second. This was possible as by that time the speed of light in vacuum could be measured precisely as c is equal to 299,792,458 meter per second. Some typical distances or lengths are given in table
method for measurement of length. Dear friends, we are aware of some direct methods for the measurement of length. For example, a meter scale is used for lengths from 10 raised to minus 3 meter to 10 raised to 2 meter. A vernier caliper is used to measure length to an accuracy of 10 raised to minus 4 meter. A screw gauge and a spirometer can be used to measure lengths as small as 10 raised to minus 5 meter. To measure lengths beyond these ranges, we make use of some special indirect methods. Large distances, such as the distance of a planet or a star from the Earth, cannot be measured directly with a meter scale. An important method in such cases is the parallax method. To measure the distance d of a faraway planet S by the parallax method, we observe it from two distinct positions or observatories A and B on the Earth, separated by a distance AB is equal to B at the same time as shown in this figure. We measure the angle between the two directions along which the planet is viewed at these 2 points. The angle ASB, represented by symbol theta, is called the parallax angle or parallactic angle. As the planet is very far away, B upon D is much less than 1, and therefore theta is very small. Then we approximately take AB as an arc of length B of a circle with center at S and the distance D as the radius. AS is equal to BS, so that AB is equal to B, that equals to d theta, where theta is in radians. D is equal to B upon theta. Having determined D, we can employ a similar method to determine the size or angular diameter of the planet. If D is the diameter of the planet and alpha the angular size of the planet, that is the angle subtended by D at the Earth, we have alpha is equal to D upon D. The angle alpha can be measured from the same location on the Earth. It is the angle between the two directions when two diametrically opposite points of the planet are viewed through telescope. Since D is known, the diameter small d of the planet can be determined using alpha, which is equal to small d upon d.
Measurement of distance to stars. Sun is the star which is closest to the Earth. The next closest star is at a distance of 4.29 light years. The parallax measured from two most distant points on the Earth for stars will be too small to be measured, and for this purpose we measure the parallax between two farthest points, that is 2 AU apart, along the orbit of the Earth around the Sun.
Subscribe to my channel. Click on bell icon to get notification about new video.